In this video, we'll learn how to convert between Kc and Kp. A mass action expression shows how the amounts of reactants and products are related to one another. And when we write this expression, we can do so with either pressure or concentration units. If gas pressures are used, the constant is called Kp, and if molarities are used, the constant is Kc. The Kp equation relates the two equilibrium constants when the pressure units of Kp are in atmospheres. This form of the equation is used to solve for Kp, but we can also rearrange it to solve for Kc. Be careful with the exponent delta Ng. It is calculated as the moles of product gas minus the moles of reactant gas, using the balancing coefficients from the chemical equation. The value can be positive, negative, or 0. If the value is 0, then notice from the Kp equation that RT is raised to the 0, which equals 1. In this case, Kp equals Kc because the RT term drops out of the equation. You'll see that I tend to show the calculations of the RT term separately. I do this for a couple of reasons. First, I want to make sure that T is in Kelvin. I can confirm this by checking that the temperature units cancel in the RT term, even though we don't really deal with the other units, because Kp and Kc are unitless. The other reason is to ensure that the math is done correctly. The delta Ng exponent only applies to the RT term, not the Kc. So let's work a problem. In this example, we're given a value of Kc at a certain temperature, and we're asked to calculate Kp. I'm going to start by writing my Kp equation. Kp equals Kc times quantity RT raised to the power of delta Ng. I like to write the equation first because it reminds me that there are a couple of things I need to calculate before I use the equation. The first is the temperature in Kelvin, and the second is delta Ng. Calculating the temperature in Kelvin, I have my degrees Celsius, 1227 plus 273.15. This is an addition, and so I need to keep track of the decimal places for my sig figs. 1227 has sig figs at the ones place. The 273.15 is exact, so I need to round my temperature in Kelvin to the ones place. Doing the math, 1227 plus 273.15 rounded to the ones place gives me 1500 Kelvin. I need to make sure that I put the terminal decimal point there to signal that those zeros are significant. The next thing I do is calculate my delta Ng. So I take my moles of product gas, so I have 1 plus 1, minus my moles of reactant gas, which is 1, and that gives me a value of delta Ng of plus 1. So the next thing I'm going to do is calculate my RT term. R is 0.08206 liters atmospheres per Kelvin mole. I do like to include the units here because, as I mentioned in the introduction, it reminds me that my temperature needs to be in Kelvin. I can cancel those units and then basically ignore the rest of them. So R times 1500 Kelvin. For sig figs, R is exact. I have 4 sig figs in my temperature, so my RT term will be rounded to 4 sig figs. Doing the math, 0.08206 times 1500 rounded to 4 sig figs gives me 123.1. And now to use the final equation, I have Kp equals Kc, which was given in the problem, 3.10 times 10 to the negative 6, times RT raised to the 1, 123.1 raised to the 1. This result will have 3 sig figs based on the Kc. Doing the math, 3.10 times 10 to the negative 6 times 123.1 gives me 3.82 times 10 to the negative 4. In our next example, we're given equilibrium pressures in atmospheres, and we can use those to calculate Kp and then convert to Kc. So to set up the mass action expression, we set it up the same way as we do for Kc. So I have Kp equals the pressure of HNO3 squared times the pressure of NO divided by the pressure of NO2 cubed times the pressure of H2O. Plugging the numbers in, I have 0.0110 for HNO3, that will be squared, times 0.0127 for NO, divided by NO2, 0.0971 cubed, times H2O, 0.154. As far as sig figs, it looks like we have 3 sig figs everywhere, and so our final result will be rounded to 3 sig figs. Doing the math, we have 0.0110 squared times 0.0127 divided by parentheses 0.0971 cubed times 0.154, close out the parentheses. Rounding to 3 sig figs, we get 0.0109, and that's Kp. Next, we're going to solve for Kc using a rearranged form of the Kp equation. So let me write down our regular form. Kp equals Kc times RT raised to the delta Ng. To rearrange this to solve for Kc, I just need to divide by the RT term, and that gives us Kc equals Kp divided by RT to the delta Ng. So just like the last example, I need to calculate my temperature in Kelvin and my delta Ng. My temperature is 25 degrees Celsius plus 273.15, rounded to the ones place, will give me 298 Kelvin. For delta Ng, for my product gases, I have 2 plus 1, minus my reactant gases, which are 3 plus 1. 3 minus 4 equals -1. Next, I want to calculate my RT term. So I have 0.08206 liters atmospheres per Kelvin mole times my temperature in Kelvin, which is 298. Making sure my Kelvins cancel, I'll end up with 3 sig figs for my RT term. Doing the math, 0.08206 times 298 to 3 sig figs gives me 24.5. And now plugging everything into my rearranged equation, I have Kc equals Kp 0.0109 divided by RT 24.5 raised to the -1, because that was my delta Ng. 0.0109 divided by 24.5 raised to the -1 gives me 3 sig figs 0.267.